Hi everyone. In today's video, we're going to talk about MLP-Mixer. I'm going to read the architecture from the paper, then I'll run a small experiment using CIFAR-10 dataset. So let's get started. So this is the paper MLP-Mixer, an all-MLP architecture for vision. Let's jump over here and read this paragraph. Modern deep vision architectures consist of layers that mix features I at given spatial location, I between different spatial locations or both at once. So we are mixing features at a given spatial location. A spatial location is the patch. When we cut an image for a vision transformer, one patch is a spatial location or between different spatial locations. So are we either mixing features between different locations or at the same location. In CNNs, the convolution neural nets, II is implemented with n by n convolution for n is greater than 1 and pooling. Neurons in deeper layer have larger receptive fields. At the same time, one by one convolution also perform I. So if we design the convolutional neural layer to take only one by one filters, basically we are mixing the features at the same pixel. We are not considering all the neighboring pixels. And larger kernels perform both I and II. In vision transformers and other attention-based architectures, self-attention layers allow both I and II, and the MLP blocks perform I. Different architectures are doing different things, whether to mix features at the same spatial location or between different spatial locations. The idea behind the mixer architecture is to clearly separate the pair location channel mixing. That channel mixing operations is where we mix features at the same spatial location at the same patch, and cross-location token mixing operations II. Both operations are implemented with MLP. Figure 1 summarizes the architecture. The idea behind this architecture is to make a clear distinction between channel mixing, where we are mixing features at the same spatial location, and token mixing, where we are mixing features between different spatial locations. So the architecture is illustrated here. So we're cutting the image into patches and we're feeding the patches into n mixer layers. These are the mixer layers. So the image passes through a layer node. These are the patches in the image and these are the channels. First, we are passing the patches, we're transposing the tensor, and we're passing the patches through an MLP. Basically, we're doing the channel mixing. Then we're putting the tensor in the original shape at the layer norm, and we're passing the channels. Both tensors pass the same MLP. Fully connected layer, nonlinearity using GLO, and another fully connected layer. And there are skip connections in the architecture. So this is the general architecture. It's very simple to understand, and there are no hierarchical. We'll talk about the hierarchical features at the end. They did some experiment with hierarchical features. We will talk about that at the end. So here they are saying that in the extreme case, our architecture can be seen as a very special CNN, which uses one by one convolution for channel mixing and single channel depth-wise convolutions of a full receptive field and parameter sharing for token mixing. So these are two special parameters that makes MLP-Mixer a convolutional neural net. However, the converse is not true, as the typical CNNs are not special cases of mixer. Furthermore, a convolution is more complex than a plain matrix multiplication in MLPs, as it requires an additional costly reduction to matrix multiplication and or specialized implementation. So here they are arguing that in the MLP-Mixer, the architecture only contains linear layers, uh, the basic MLPs, and no convolutional layers, which require either costly reduction to matrix multiplication, the using image to column operation, or specialized implementation. And that argument is pretty solid. Just look at the code they provided in the appendix. This is the MLP-Mixer code written in JAX and FLAX. It's only three classes: MLP-Mixer, which calls mixer block, which calls MLP block. We'll look into the code, but that's it. It's only 40 lines of code. So we will look into this architecture. I'll jump into the code. By the way, you can find the original implementation here in this repository. the Vision Transformer repository. They have all the implementations, the original Vision Transformer and MLP-Mixer, and the following up works. In the acknowledgement, I borrowed some code from this repository. I also borrowed some code from this course website, and I got some code by prompting Gemini, so thanks for the developers that made their code available. Here is the reference for the MLP-Mixer. I'm just installing MLP collection because I needed to initialize the model. These are the libraries. I'm running this notebook in a TPU environment. So I run the jax.local list devices and it shows 8 devices. This is the configuration for CIFAR-10 dataset. 10 classes, 128 batch size, 100 epochs. The layering rate is 0.001. The width of the image is 32 pixels. The height of the image is 32 pixels. And these are the means, the channel means for images in CIFAR-10 dataset. And this is the standard deviation. I need these values to normalize the images in CIFAR-10. And these values for just changing the training the images by randomly cropping and resizing the training images. I'm importing CIFAR-10 dataset using torch vision. And these two helper functions will help me to make a data loaders with NumPy arrays. And this function here will normalize the images. So I'm downloading the training dataset and I'm splitting it into a train set and validation set. And I'm also downloading the test set. For the test set, I'm performing test transform, which only converts the image into NumPy. But for the training dataset, I'm doing train transform, which performs horizontal flip and performs the cropping, the random cropping. So at the end, I'll have a train data loader, validation data loader, and test data loader. And here is the size of the first batch. 128 images, 32 by 32 by 3 channels. The data type is float 64, and the labels is 128 labels with the data type int64. And this is a helper function just to get the labels for CIFAR-10 dataset. I got this function from the Vision Transformer GitHub repository. I think they have it in one of the collab notebooks. Here in the cell, I'm pulling the first 10 images and their labels: frog, bird, ship, frog. And another cell, because I don't trust the first 10 images, I'm just pulling random images, random 10 images, just to check the labels actually align with the images. So this is an automobile, this is a dog, bird, truck, an automobile. Yeah. So the labels are the labels are correctly aligned with the images. And this is MLP-Mixer class. Basically, this cell is this code here. I copied it from the Vision Transformer GitHub repository. I have another notebook with the print statements inside the MLP-Mixer class. Here I have print statements just to check how the tensor changes shape during training. We will look into those, but first I'll just have to finish with the training setup for JAX. So this is a train step. It has a loss function, and here I'm just pulling the logits from the model. I'm converting the label and converting them into one hot label, and I'm computing the loss between the one hot labels and the logits, and I'm returning the loss. This function here will create a train state for FLAX. So I'm initializing the model with the 4x4 patches, and the number of classes is 10. The number of blocks for the mixer blocks is 8. The hidden dimension is 192, where the hidden dimension for the channel, and for the token MLP dimension is 96, and for the channels the MLP dimension is 768. I'm getting these numbers by just dividing the numbers in the. So if you go to Vision Transformer VIT JAX complex models.py, here are the parameters for the MLP-Mixer. And because they're taken 16 by 16, I divided that by 4. I divided everything else by 4. I just kept this one here by is 8. I divided this by 4, and I divided this number by 4. For sure, these numbers need tuning, but it's good enough just to initialize the model. So here I'm initializing the model with the learning rate and random weights, and this is the training loop. Before we continue with the training loop for 100 epochs, in this notebook, I run only one epoch with the print statement. I'll look into that and see how the tensor changes shape during training. So here I'm putting print statements everywhere. So let's check out the output. It's basically the same notebook, but I put 2 breaks here just to see only the first batch. So this is a printout. The first print statement show that tensor size is 128, 32, 32 by 3. And this is just the first 128 is the batch dimension, the 32 is the height, the second 32 is the width, and the 3 is the RGB channel. Then we are getting 128 by 8 by 8 by 192 just after stem. And this is the layer for the convolutional layer here. This is the layer stem. So this layer is basically, we are starting the convolutional layer that the hidden dimension is 192. Did that by when we initialize the model here. The hidden dimension is 192, which is, by the way, in the architecture and the paper here. This layer here is the convolutional layer, and this is the hidden dimension that we set to 292. And we are telling the convolution layer that the batch size is 4 by 4 and the strides is 4 by 4. So basically cut the image into non-overlapping patches and map those patches into the hidden dimension. So 4 by 4, because we have 32 pixels, over 4 we will have 8 patches along the height of the image and 8 patches along the width of the image. And each image will have 64 patches. So 8 by 8, and the channels are 192. Then we are seeing that after rearrange, we are reshaping the tensor to 128 by 64 by 192. Basically, we are flattening the height and width dimensions. It's done here. This line of code here flattens the height and width. And I found this library INOBS more readable than reshape, than tensor reshape. And it's increasingly used and adopted in more GitHub repositories. It's more readable. Just look by this. So this is the previous shape, and this is the new shape, and it flattens these out. The nn.conf produces a tensor of size 128 by 8 by 8 by 192. By flattening these, we will have a tensor of size 128, 64, and 192, which is the input to the mixer block. Now, the next print statement produces block 0, which is the start of the mixer block. And the shape, it's the same shape, the same as the input. Now we are performing the swap access. We are bringing the channel dimension to be the second dimension. So it will be patch by channel by tokens or patches. So this is what's happening here. Inside the mixer block, first we are swapping the dimension. We are bringing the channel dimension to be the second dimension. Then we are passing that to the MLP block. The MLP block will receive a tensor shape 128 by 192 by 64. Then it will perform a linear layer that wraps the 64 into 96. Then it will return the 96 to the original 64 using another linear layer, and it will return that tensor. Performs the linear layer using MLP dimension, which we set to 96. then it performs a nonlinearity, then it retains the tensor to the same shape using another linear layer, and it will return that tensor. So basically we're passing, this is token mixing, this tensor here into a dense layer, and the 64 got mapped into 96. We perform a nonlinearity and another dense layer to return it to the original shape. Then after that, it will get out of the MLP block, and this is the tensor shape. Then we will swap the dimensions again to bring the tokens to the second dimension, and we will get into the MLP block again. The channels will be mapped for 192 to 768 and another layer to return them to 192. So we swapped the dimension after the MLP block, after token mixing. We swap the dimension to the batch, tokens, channels, and we feed that into the dense layer, which will map the 192 to 768 nonlinearity and another linear layer to be of the original shape. And it will get out of the MLP block, and it will get out of the mixer block, and it will start another mixer block. So this operation here, this operation, swapping dimension, token mixing, swapping dimension, channel mixing, this operation will be repeated for all the 8 blocks. It is the same operation, the same sizes. It didn't change the size. The same channel size, the same token size. At the very end, we are averaging, we are performing layer norm, and then we are averaging across the token dimension. Here we are averaging across the token dimension to get a tensor shape 128 by 192. Then we are using a linear layer to predict the classes, and it will produce a tensor of size 128 by 10. So this is actually what's happening inside the MLP-Mixer. It's basically transposing MLP, transposing another MLP. And at the end, we will get the predictions. One thing I would do as a researcher, or the first thing I would do as a researcher, is just to ask how this architecture will change if we add a resolution. So if we merge tokens, just like in Swing Transformer, actually they addressed that in the appendix. I like that, the things that did not help. So they talk about pyramids. All layers in the mixer retain the same isotropic design. We tried using the token mix in MLP to reduce the number of tokens by mapping from S. S in our case is just 64. By mapping from S input tokens to S prime, where S prime is less than S output tokens. While first experiment showed that on GFT300M, such models significantly reduced the training time without losing much performance, we were unable to transfer these findings to ImageNet or ImageNet 21K. However, since pyramids are popular design, exploring this design for other vision tasks may still be promising. So here they're saying that it did not help merging tokens, but they did not rule out exploring this design further. And it's been almost more than 3 years since this paper came out, so I'm sure that there are follow-up works that address this, but I haven't looked into that. But it would be interesting. Now let's get back to the training loop. So for a number of epochs, I'm printing the training loss and I'm printing the validation loss. And this is, so the initial loss was 1.75, and after 100 epochs, the train loss was 0.03. So I just pulled 10 random images from the test set and see how the model will predict on those. So I got this wrong. This is a dog. It was predicted as a cat. This is true. This is a ship predicted as a cat. This is true, true, And this is a dog that was predicted as a cat. And here a horse that was predicted as a cat. And the confusion matrix. So this is the confusion matrix, and the overall test accuracy is 75%. So actually I run it twice. Once for 10 epochs and I got 73%, and for 100 epochs I got 75%. Uh, my gut feeling is that these parameters that I'm starting with are not ideal for CIFAR-10 dataset, and I have to just play with these and just tweak these three: the hidden dimension, the tokens, MLP dimension, and the channels MLP dimension. I have to look into specific implementations for CIFAR-10 dataset and see how to set these parameters. Just a note about the MLP-Mixer. This is the architecture for the ResNet. Convolution layers with the residual connections, and each dotted residual connection changes the shape of the tensor. So we are increasing the receptive field. So this is ResNet, and this is the architecture for vision transformer, and this is the architecture for swing transformer, and this is the architecture for MLP-Mixer. If I had to start, or I had to code one of these architectures in a low level language, I would choose the MLP-Mixer. I'm not sure if it's the most efficient one, but for sure, it's the easiest one to implement. It's just a transpose, matrix multiplication, another transpose, and that's it. It's the attention layers are not there, and the receptive fields, the increasing receptive fields, and the batch merging is not there. So the simplicity of this architecture, and I saw some of the downstream tasks in computer vision, just like the point tracking tasks. They are using the MLP-Mixer. They are the efficiency is the is very important for these tasks. That's it, guys, for today's video. If you find this video helpful, please like and subscribe. I'll make sure to put all these commands and these notes into one blog post and share it with you guys. Thanks for watching. Bye.